Okay, so hello everyone. This seminar this month will be given by Professor Frederico Guimarães, and he is a professor and head of the laboratory that we call MINDS. It's Machine Intelligence and Data Science in Brazil, and he is a faculty member of the electrical engineering in UFMG in Brazil. His topics of interests are computational intelligence, time series, all kinds of optimization aspects. He has more than 200 publications in very good journals and very high quality conferences. And he is an editor in two very prestigious journals, Neurocomputing and IEEE Access. So I'll transfer the baton, that's how we say it in Hebrew, to you, Frederico. I want to thank all the people that joined us, colleagues from our department and colleagues from Braude. I invited a very special student, a PhD student from Harvard in math and economics to join us, that we might all in some point collaborate. So it's a good platform for all of us. So please, Frederico, and thank you for joining us and giving this great talk. I will share. I'll give you I'll make you a co-host, and the platform is all yours.
Okay, let me see. How can I? Yeah.
You have to share your screen.
I think you can see the.
Yes, we can. Yes, we can.
Okay, so thank you very much, Miri, for the invitation and for the kind introduction. For me, it's a great satisfaction to have this opportunity to give this talk here and to see some friends from Braude College. It's almost 10 years that I've been in Israel and visited the Braude College, so I'm very happy to give this talk, to have this opportunity. So in this talk, I'm going to talk about new developments in fuzzy time series methods, and most of these developments that came from research in our lab, machine intelligence and data science. Sorry. So the summary of this presentation, I will start with a brief introduction and the basic idea of fuzzy time series, these developments on fuzzy time series in the last years. And also I will conclude presenting the pyFTS library, which is a Python library for FTS developed by the students in our lab. So time series is becoming more and more important nowadays, basically, especially because of some driving technologies that are generating and gathering a lot of data indexed by time. I can mention the industrial networks, sensor networks, edge computing, smart sensors, of course, IoT and IoE. IoE is the Internet of Energy, it's the application of IoT for smart grids. And also in health monitoring, we have some smart devices that are generating and sensing data of our health condition all the time. And the availability of all this data requires methods for analyzing and predicting and classifying this time series data. In the context of IoT, we have these characteristics of high frequency sampling data, large data volume, usually high dimensionality in terms of number of variables that we are monitoring, and also changing environments, non-stationary environments. All these characteristics require methods that can be adapted to these features. Fuzzy time series is an emerging class of forecasting methods. They were introduced back in the 1993 by Song and Chissom. The seminal papers are mentioned here in the bottom of the slide. However, the model initially proposed by Song and Chissom required some complex calculations due to the way that they calculated the composition operators. And a more simplified model was then proposed by Shen in 1996. And this model became very popular because it was very simple to compute and to implement. FTS are forecasting models based on rules, which are then extracted from the fuzzy representation of the original data. It can deal with discrete or continuous data, and it can process non-fuzzy and fuzzy values. Also, a very nice characteristic is that they are interpretable and transparent models for forecasting, which is becoming relevant nowadays in the field of explainable AI. So this is a brief introduction to fuzzy sets and fuzzy systems, just to give the background. So in comparison to classical sets, elements of fuzzy sets have membership degrees to the set. So they have continuous membership degrees to the set. And this degree of membership indicates the degree of certainty that a given element belongs to the set. So every fuzzy set is characterized by a membership function, which maps elements of the set to a continuous values between 0 and 1. Fuzzy sets can be discrete or continuous, can have discrete or continuous domains. The representation of a fuzzy set with discrete domain is shown here. We have a collection of elements x1, x2 until xn, and each element with an associated membership degree to the set. We can synthesize this notation using the summation operator, but I remark that this summation operator is not a sum. Actually, it's just to represent that we have a collection of elements with their corresponding membership values. For a continuous set, we have a continuous domain X, and then we replace the summation sign by an integral. But again, it's not an integral, it's actually a collection of members to a set. The universe of this course is the domain of a given variable or a linguistic variable A. The partitioning of this universe of this course is a division of the domain into overlapping intervals. And then we associate a fuzzy set to each interval. So we have, for each interval, we define a fuzzy set in a way that the union of all intervals become the universe of discourse. Here's an example. We have a linguistic variable called temperature and 7 linguistic values for this variable. And each linguistic value is represented by a fuzzy set, in this case a triangular fuzzy set, representing the degree of membership of values in the interval to the linguistic value. So here we have 7 fuzzy sets, each one representing a concept, let's say very low, low, average, and so on. For fuzzy system, the dynamic behavior of the system is then characterized by fuzzy rules. And these fuzzy rules have a format like the one shown here. We have, if input X is AI, then output Y is CJ, and AI and CJ are both fuzzy sets. The fuzzy sets and the fuzzy rules make the knowledge base of a fuzzy rule-based reasoning system. And the components that we have in this fuzzy reasoning system are fuzzification, inference, and defuzzification. In the fuzzification step, we receive non-fuzzy inputs or numerical inputs, and then we fuzzify these inputs, calculating the membership of the values to the fuzzy sets. For the inference, we compute, given the fuzzy sets and the rules, we compute the results in linguistic values by applying the rules, okay? And then, given the outputs, the fuzzy outputs, we convert them back into numerical values. This process is called defuzzification. The basic idea of fuzzy time series method, actually considering the Shen's method, is simplified in the following steps. So we define the linguistic variables of our problem. We define the universe of discourse and number of partitions. We apply a data partitioning method to partition the universe of discourse into intervals. And for each partition, we define a fuzzy set. Then for fuzzification, we obtain a fuzzy time series representation of the data, of the numerical data. Given this fuzzy time series data, we find these temporal patterns, the transitions that occurred in the historical data, and we call them fuzzy logical relationships. And from these, we formulate the fuzzy rules. By applying the fuzzy rules identified in historical data, we then generate, and using the fuzzification, we generate the non-fuzzy outputs of our model. Here is an example of this process. Let's say we have a time series Y, whose universe of discourse is a subset of R. So we have the axis here representing the range of variation of the time series Y. And on this, and we define fuzzy sets on this universe of discourse, on this range. Ft consists of a sequence of fuzzified values of Y. So Ft is called a fuzzy time series defined on Y. So Y on the left is our original fuzzy time series, and on the right, through the process of fuzzification, we have a sequence of fuzzy sets, which is called the fuzzy time series. Given this sequence of fuzzy sets, we can identify the transitions that were observed in the historical data, as shown here. Here is an example I took from the paper below, on the bottom, and it's enrollment data of a University of Alabama. So it's the number of registrations in each year and the fuzzified value in the third column. And from this historical data, we can identify the transitions. So A1 goes to A1 and so on, A1 goes to A2. So we list all the transitions observed in the data. And then we group these transitions by the left-hand side, by those transitions that have the same left-hand side. So it's shown in table 8 here. So for instance, whenever we have an input that belongs to A4, the next value will belong to either A4 or A3 and so on. After we have identified these fuzzy logic relations from the data, we have the model, we can build the fuzzy rules. So each rule has the format, a left-hand side that implies in a right-hand side. The left-hand side takes, for a high order model, takes all the legs, the p legs of the input, And for each leg, we see what fuzzy set this leg belongs to. And on the right-hand side, we have the possible fuzzy sets that come in the sequence. Okay? So the left-hand side is used to match the input patterns, to identify the input patterns to that fuzzy rules. And the right-hand side is used to forecast the future values, considering the possible fuzzy sets that we have in the consequent. So the list of these fuzzy logical relation groups here can be represented in a table, for instance. This is for one order model. We have on the rows the left-hand side, and on the columns the right-hand side. So we can identify the transitions. Whenever the input is, let's say, A4, the next value in the sequence could be A3 or A4. Okay, so these patterns that are identified in the historical data, they can represent in this table, but they become the knowledge base of the model. Once the rules have been obtained, they form the knowledge base, as I said. And the forecasting procedure is given below. So we fuzzify the input, we find the active fuzzy rules in the knowledge base, given that input. In other words, we match the fuzzified input with the left-hand side of the rules. And then for those rules, we compute the output and then defuzzify by generating a non-fuzzy forecasting value. So this is the basic idea of fuzzy time series, especially following the method proposed by Shen. And as you can see, there are many many variations that can be implemented for each of these steps. Let me show here how we can defuzzify the outputs, for instance. If the right-hand side is empty, in other words, there are no rules for this input, then we use a naive forecast. We take the midpoint of that fuzzy set. If the right-hand side has only one set, we take the midpoint of that set, AJ, for instance. If the right-hand side has multiple sets, there are multiple possibilities for the consequent, then we take an average of the midpoints of each fuzzy set. These sets can be weighted according to their frequency in the training data, so we can define weights for each possible fuzzy set in the output. Let's say here for A4, we have 1/3 for A3 and 2/3 for A4, for instance. So this is the basic idea. And why using fuzzy time series? Well, these are some good characteristics of these methods. First of all, they present very good accuracy in many problems. They have a low computational cost. The models are quite fast to compute. They can be applied to both small and large data sets. This is a drawback of deep learning, for instance, in which we need large data sets to train the model. It has a good explainability because we use linguistic variables and fuzzy rules, so that the model is easy to understand. It's a data-driven and non-parametric model. It's simple and flexible. Given this flexibility, as I show here, we have many variations of the basic model. So, for instance, we can have a time invariant or time variant model. In terms of number of variables, univariate or multivariate, the way we fuzzify the inputs, the methods that we can apply for partitioning the universe of discourse, the order of the model, the fuzzy sets that we use. The different types of fuzzy sets have been proposed in the literature. The knowledge base, I shown the knowledge base represented as a matrix, but we can use rules, neural networks, and other models. The methods for defuzzification, transformation of data, and so on. So this diagram tries to show the number of variations that have been proposed in the literature in the last years. There are some open issues regarding fuzzy time series. I have identified some here. First of all, there are many univariate methods available, but only few multivariate methods. There is a lack of multivariate forecasting, considering multiple inputs and multiple outputs. The scalability to big data applications, the use of the possibility of interval forecasting and probabilistic forecasting. There are few time variant models and few FTS models to deal with non-stationary data. In some applications, especially when we have many variables and large data sets, it's hard to find the FLRs from the training data. FTS models for dealing with stream data and changing environments, which is becoming more and more important in IoT applications. And also some hybrid models with statistical methods and other machine learning techniques. Well, in the last few years, our lab has presented some developments that are related to these open issues, which I'm going to discuss next. So the first model that I would like to present is the exponential FTS. The reference is on the bottom, which was published in International Journal of Approximate Reasoning. And the idea of this model is to give more weight to recent historical observations, especially in the stock market forecasting. It makes more sense to give more weight to those observations that are more recent. PSO is used as a method to determine some parameters of the model, particularly the optimal lengths of the intervals and the weight parameters of the model. So given this FLRG, we produce the following, propose the following output. We have the midpoints of each fuzzy set in the right-hand side, but these midpoints are weighted by weights beta that decrease exponentially. And the parameter of this exponential decrease, which is xi, is found through optimization. Okay, so for each FLRG, we have this exponentially weighted output. So this is the diagram taken from the paper. We have the first phase. We recognize the universe of the scores. We partition into equal intervals. We apply the Shen's method on these intervals and apply an optimization engine, in this case PSO, to optimize the lengths of the intervals. Once we obtain the optimal lengths, we go to phase 2, in which we optimize for the parameters of the exponentially weighted model. We also propose some hybrid models combining classical statistical methods with fuzzy time series. The first paper that proposed this combination was by Egrioglu. He proposed an ARIMA and SARIMA model combined with high order FTS. Later in 2016 and 2017, we proposed a hybrid model of RFIMA and SARFIMA and high order FTS for long memory time series. So the fuzzy forecast output combines the ARFIMA model and the FTS model. The parameters of the ARFIMA model are estimated by PSO optimization. We validated the model with some financial time series and also with load forecasting data. So the usual FLRG in high order model is shown here. We have the P legs of the fuzzy time series in the input in the left hand side, and the consequent on the right hand side, the next value FT. In ARFIMA FTS, we modify this FLRG to the following symbolic structure. We have a number of legs of the input. The maximum leg is found through partial correlation, for instance. And we have the consequent, the possible fuzzy sets in the consequent. Okay. Then the fuzzified output is a combination, is a linear combination of the parameters of ARFIMA model, here, the first term, and the midpoints of the fuzzy sets in the consequent, as shown here. So the output is a linear combination of the ARFI model and the FTS model. The parameters of the ARFI model and this alpha coefficient, they are found through optimization using the training data. After we compute the ARFI model, we can then calculate the moving average part in training data to obtain the complete model. The whole process is shown here. We first compute the ARFI part of the model using the optimization by PSO to find the parameters of the model. Then, after we obtain the ARFI part, we can go to the phase 2 and compute the moving average part of the model. And then we get the complete model, the complete ARFIMA or seasonal ARFIMA model. Another model that we proposed in this paper in 2020, last year, is a new weighted multivariate model, which included some methods for distributed training and forecasting. The method was designed to allow several models to be trained individually with subsets of data. So your data can be divided into different machines, and each node can compute a submodel. And later, these submodels can be merged into a single model. Since FTS is a fuzzy rule-based model, it's easy to make this process, to combine models into a single model. The distributed approaches were implemented using map-reduced paradigm over GSPI open source clustering infrastructure. We also proposed in this paper a hyperparameter tuning method using genetic algorithms. So this genetic algorithm, also distributed one, was used to fine-tune the hyperparameters of the model using distributed data. The final model consists of a set of variables V, a fuzzy linguistic variable VI for VI tilde for each variable in the set of variables, and a set of weighted fuzzy rules. I will not go into details of this diagram, but the rule in the induction step is modified to this. So we have the fuzzy temporal patterns associated with the fuzzified values of the variables. So we have, for each variable, V1, V2, up to Vn, we identify the fuzzy set, corresponding active fuzzy set for that variable. So this is the left-hand side. And then right-hand side has the fuzzy set of the variable, the target variable. We group all the temporal patterns with the same left-hand side, and also use weights for the right-hand side. Okay, these weights are the normalized frequencies according to historical data. So given this model, we can compute the output, the diffusified output, by taking the average, the weighted average of the midpoints, weighted by the activation weight of each rules. So the summation here is done in the rules. And the midpoint here is computed through the weighted sum of the centers of the fuzzy sets in the right-hand side. This is the process of distributed training using MapReduce. So we have the first phase, we use MapReduce to compute the partition of the universe of this course and obtain the fuzzy sets, considering that we have a data slice in each different nodes. And in the second phase, we compute the fuzzy rules in each node and use the reduce step to merge these rules into a single model. We also proposed in 2019 a multivariate model that uses fuzzy information granules. pyFTS was proposed with the goal of transforming a multivariate time series into a univariate FTS by using these fuzzy information granules, which are multidimensional fuzzy sets. So the idea is that in multivariate time series, we use these fuzzy information granules to represent the multivariate time series in a multidimensional structure. A granule can be seen as a multivariate fuzzy set, where each variable is related to a time series. It's then a high order model for both multiple input, single output, and multiple input, multiple output models. It's easy to adapt for other univariate FTS models because we convert the multivariate time series into a sequence of multivariate fuzzy sets. So we can easily apply other FTS methods to this model. So considering a multivariate time series Y with m variables, m time series, for each time series, a corresponding linguistic variable is defined. So we have, for variable Vi, the fuzzy sets Aj of this variable, creating a partitioning for that variable. The combinations of fuzzy sets from all variables represent the information granule. So we have a granule GK combining the fuzzy sets of each variable for all variables. And the membership function is minimum T norm considering this granule. So given these ideas, we have the pyFTS model, in which for forecasting, we first apply rule matching. To optimize the process, we use KD3 to index the centers of the granules in the multidimensional space. We find the K rules closest to the input pattern, and then by taking these rules, we defuzzify the output, calculating the mean points of the fuzzy sets in the right-hand side, and then calculating the weighted sum of the mean points. Okay. We applied this model to chaotic time series in this paper, and also to some energy data. GEFCON 12 benchmark data is a benchmark using solar energy temperature data for forecasting. Here are some results shown in the paper. We have in blue the original time series. We have 3 variables, right? In orange, the forecasting for 1 step ahead, and in green, the forecasting for 200 steps ahead. Finally, I present the evolving multivariate FTS. It's a model developed by a PhD student in our lab, and we had the collaboration of Miri in advising the student. So the evolving multivariate FTS was conceived from the integration of high-order FTS with an evolving clustering algorithm, particularly the microtheta class, which is this evolving clustering algorithm that we proposed in this paper here in Future Generation Computer Systems Journal. So the method can deal with a high volume of non-stationary spatial temporal data arranged as multivariate time series. The model has the ability of adapting to online or stream data, adjusting the parameters, sets, and rules of the knowledge base. So it's a dynamic model, and also it has scalability because it uses an evolving stream clustering method to find the fuzzy sets. So here's the idea. We have a multivariate time series. Here I show 2 time series. Each, the values of the time series for each timestamp make up a point in the multidimensional space. These points are clustered using an evolving clustering method, evolving clustering algorithm. These clusters identified by the method are then used to generate the multidimensional fuzzy sets. And as we have the multidimensional fuzzy sets, we can observe the sequence of transitions in the model and then find the fuzzy logical relationship groups. And this is the knowledge base of the model. And as the data is received in a streaming way, the clusters change, they evolve in time, and therefore the fuzzy sets evolve in time and the fuzzy rules of the model. So the model is constantly evolving as data is being received. This model has been just submitted to Renewable Energy Journal this year. Here are some results that we presented in this paper. Results on solar and energy forecasting data. We take measurement data from 16 sites so we have 16 different locations of measured data, and we use all these measurements to compute the forecasting for a given site. So this is why it's a spatial temporal model and multivariate as well. So here are the results of the evolving model here on the left compared to vector autoregression, neural networks, and the FIG-FTS that we proposed. Also, we proposed a probabilistic forecasting model in this paper for IEEE transactions on fuzzy system. Probabilistic forecasting is a class of forecasting in which the method provides either intervals, not only the point forecast, but also intervals of confidence and also probability distributions as the outcome. In this paper, we propose the probabilistic weighted FTS, which is capable to provide forecasting for one step ahead or many steps ahead, intervals and probabilistic distributions. The method does not make any assumption about the data, and it's computationally fast. It's the first FTS method in the literature that integrates point, interval, and probabilistic forecasting. Based on many experimental results that we show in this paper, it's the state-of-the-art method in FTS literature. In this paper, we compare the model with many statistical models and many FTS models in the literature, showing very strong results. I will not spend much time here, but just show the knowledge base of the proposed model. So in the left-hand side, we have the fuzzy sets in the left-hand side, weighted by the empirical probability of that fuzzy set. In the paper, we show the details, how we can compute this empirical probability, but it's basically the probability of that fuzzy set occurring in the left-hand side, given historical data. And on the right-hand side, we have the weighted contributions of the fuzzy sets in the consequent, okay? And we show that this model can compute probability distributions and prediction intervals and so on. I recommend you to see the details in the paper. So back to the open issues that I mentioned in the beginning of the presentation, I would like to highlight where these contributions, how these contributions are related to these open issues. So for multivariate models, we propose the weighted multivariate FTS, which also has the ability to deal with distributed training, and the FIG-FTS. They are both multivariate models. For multivariate input and multivariate output, we have the FIG-FTS model. For the scalability to big data, we have the distributed training in multiple nodes using this model. PWFTS is able to provide interval forecasting and probabilistic forecasting. For time variant models and for non-stationary data, we proposed a non-stationary FTS. I didn't talk about this model here, but this is another development from our lab. And the evolving multivariate fuzzy time series. For dealing with online and stream data, we have the evolving model. And the hybridization with statistical methods, we have the RFIMA FTS and SAR-FIMA FTS. And we are currently developing some hybrid models with machine learning techniques, with other machine learning techniques. So for the last part of this talk, I would like to present you the pyFTS. It's a Python library for fuzzy time series developed in our lab. You can see the reference here and also in the chat. So the pyFTS was developed by Minds Lab with collaboration with the Federal Institute of the North of Minas Gerais, Federal Institute of Minas Gerais, and UFMG. The library was developed in Python, and it used other libraries like matplotlib, pandas, and numpy. This is how you can install. For those familiar with Python, they know that it's easy to install using pip command. The structure of pyFTS, we have some the common part it has some common methods of FTS models. We have a number of different methods for partitioning the universe of discourse. We have different metrics for computing the errors of the model. Different models, FTS, high order FTS, Fig FTS, and so on. And we have some data available in the library for testing the models. And they come from financial time series, chaotic time series, and so on. The training process of the training process using pyFTS is quite simple. First, we need to define a partitioner. So with this line, we define, for instance, the grid partitioner, giving as input the data and the number of partitions that we want. And then we generate a model, let's say a high order FTS, by providing a partitioner and the order of the model. Then we use model.fit, providing the data, and we generate the model. So with 3 lines of code, you can generate a high order FTS model for your data by using pyFTS library. It's quite simple to develop your model for your application. These are the functionalities provided by the library. We have a large variety of FTS models. The library provides distributed training for large data sets using the model that we proposed for this purpose. We also have point, interval, and probabilistic forecasting for one or many steps ahead, interpretability of the model, and knowledge-based visualization. The library is always updated and extended with new methods developed from research. Finally, I would like to conclude with some other papers that we developed in our lab, in our group. This is a model combining FTS with convolutional neural networks. These are some works of interval forecasting and solar energy forecasting. This is the paper in Transactions on Fuzzy Systems, in which we propose the PWFTS model for probabilistic forecasting. We have another model in pyFTS, another for probabilistic forecasting that use an ensemble of FTS models. We have distributed training for a scalable fuzzy time series. And this is a recent paper also proposing a non-stationary fuzzy time series model for non-stationary environments. So with this, I conclude my presentation. I would like to thank you all for attending this talk, and I'm available to answer your questions. And that's it. Thank you very much.
Thank you, Freddy. We can have any questions for anyone. Can you just okay? Can you hear me? Okay, I don't know if I'm heard or not. Fred, can you hear me?
Yes.
Okay.
I can
okay.
hear you.
Because when you have in some cases when you have the